Hello everybody and welcome back to another Eng 130 video tutorial. In this tutorial we're going to find another moment about a point in 3 dimensions, but as I kind of said in the last example, it's very rare that you get the force vector already in Cartesian vector notation. Now, I know that you guys are already smart and you guys already know how to find the force vector based on the magnitude and position vectors and stuff like that, but this will just be an extra example just to help you guys in making sure you guys know how to determine the moment about a point, but then it also includes just that extra aspect of finding the force vector in Cartesian vector notation. So a more complete example, if you will. So with that being said, let's get started. Alright, so looking at this example, what it would like us to do is determine the moment of the force, so F equals 600 newtons, about point A. So really quick, I think it's best if we just highlight point A, because this is the point that we're going to want to take all those moments about. So this point will be a very important parameter later on. But as I mentioned kind of before, is one of the things that we're going to want to do before this is we're going to need to find that force in Cartesian vector notation. Now to do that, what we can do is if we're given 2 coordinate points, the best way to do it is of course using position vectors. So we know that this force goes from point B to point C, and we know it goes in that direction just because the arrowhead of the force. So what we can do from there is we can say that the position vector R, and we're going from B to C, is going to be equal to the coordinates of C minus the coordinates of B. So we're going to need this position vector again because we're going to want to try and find the unit vector of that force vector, because then we can easily find the force in Cartesian vector notation. So it's going to be the coordinates of C, so in brackets really quick, I'm just going to put the coordinates of C. So first thing that we're going to want to look for is the x and the y, and in this case they're both the exact same, so it's going to be 6, 6, and there's no z component, so it's going to be 0, and then minus, and this is where it's going to get a little tricky. So you're going to have to use a bit of trigonometry to figure this one out. But if we look in the x direction, so in this direction over here, we can see that the x direction for B is going to be 4 times the cosine of 45. If we look in the y direction, so down here, it's actually not going anywhere in the y direction, that point. It's located at y equals 0. And we can finish it off with the 4 times sine of 45 for the last direction, z direction. And again, you don't have to put sine 45, you can do cosine 45 too, because in the end they're going to be the exact same answer, because the sine of 45 is equal to the cosine of 45, but you guys already know this, you guys are very smart. So we're going to move on. All I'm going to do is I'm just going to subtract them in and find out the answer. So what I get is 3.172 in the I direction, and then I get plus 6 in the j direction, and I finish it off with minus 2.828, and that's in the k direction. That's my position vector in meters. So those are the components if I wanted to get from point B to point C. But again, to find the unit vector, we're also going to need the magnitude of the position vector. But that's very, very easy once we find the position vector, because we know that the magnitude of position vector BC is going to be equal to the square root and then all of those components squared together. So I'm just going to go 3.172 squared plus 6 squared plus 2.828 squared. Just end this up very nicely. And when I type that into my calculator, I get 7.352 meters. And again, what this represents is that's the distance from points B to C. That shortest distance, if I was going directly from point B to point C, that is the distance. If I were to take a tape measure, that's what it would read out. So we can now easily find the unit vector, because we know that unit vector BC, so U of BC, is going to be equal to the position vector BC divided by the magnitude of that position vector. And we already figured out all of these, so it's as simple as just plugging in stuff. So if I were to do the vector right now, I'm just going to take all of those components that we have above and divide them by that magnitude of 7.3. So the first component I have is 3.172, and I'm going to divide that by 7.352, and that right there is in the I direction. And then I also have the j direction, so it's going to be divided by 7.352, and the j component was 6, so that's in the j. Perfect. And then I'm gonna, I'll make that a little bit nicer. Why not? Why not? And then I'm gonna finish it off, of course, with the k component. So I'm gonna have the 2.828 in the k direction, and I have to divide that by the 7.352. I'll just do that, finish off the vector. And remember, unit vectors do not have units. And it's very easy to tell from this because in these divisions right here, we're taking units of meters and we're dividing it by units of meters. So they cancel out, we get nothing. And in the end, what we get is our unit vector from B to C. So UBC is equal to, and now in brackets, I'm just going to put the actual numbers. I'm just doing the division, nothing more. 0.431 in the I direction, plus 0.816 in the j direction, and then minus 0.385 in the k direction. So all I did was divide those numbers to make it a little bit easier moving forward. So we can recall that if we want our force vector in Cartesian vector notation, so FBC with little hat, we can find it if we take the magnitude of that vector and we multiply it by the unit vector that goes in the same direction, so UBC. If we're doing FBC, it must be UBC. So we know both of these now, so we can just simply go is equal to 600, and then we can multiply it into this vector, so the 0.431 in the I direction, plus 0.816 in the j direction, minus 0.385 in the k direction. So I just wrote the unit vector again, and it's very easy just to multiply that in, because in the end what we're going to get is another vector, because this is what we want. We want it in Cartesian vector notation, of course, and this vector is 258.8. 258.8 in the I direction, plus 489.6 in the j direction, and the last component is negative 230.8 in the k direction. So we can close out the bracket, and remember that this is a force vector, so it has units of newtons. So this is more or less kind of the hardest part of this example. And if we remember, what we want in the end to determine a moment is going to be equal to r, and this r goes from the point that we want to take the moment about. So if we go up to this question, it's very specific. It says we want it about point A. So this can be r, A, and then it goes to any point on the force. And now this is where things get kind of interesting, because remember how I said last time, the position vector, it doesn't matter which point it touches the force, you can have any point, you'll get the exact same answer. And we're lucky now because we're actually given 2 points on this force. So we have two options. We can go from A to B, right here. There's one option. Or we can go from A to C. And believe it or not, those will give you the exact same values in the end. So for this first part, let's just say we pick B, because B is nice and simple, or actually B is actually more complicated. Let's not pick B, let's pick C. And the reason why I pick C is because remember, we need the position vector from A to C. So for position vectors, we need those coordinate points. So I'm trying to avoid doing the cosine and sine again at point B. I'm going to go to C because it's nice and easy. So the moment here is going to be RAC, and we're going to do that cross product again with vector FBC. So we have FBC. The only thing we're missing is this RAC right here. So we can easily figure that out though, because we know it's going to be equal to RC minus RA, which we know, I'll put the equal sign, which we know the coordinates of C already are 6, 6, 0. And we're going to subtract the coordinates of A, which we have yet to find. So looking at A, it's very, very nice. It's just 0, 0, 4. So minus 0, 0, 4. So we know that the position vector here that we're looking for is just going to be 6i plus 6j minus 4k. And that's all we need. And the nice thing about the cross product is we don't go into unit vectors. We can just deal with the position vectors. So we don't need to find the magnitude. We don't need to divide to get the unit vector. We just need this position vector. And of course, it'll have units of meters. So now looking at this formula, we have everything that we need. So I'm just going to go the moment. And remember, it'll give us a vector. So I'm just going to put the hat on top is equal to, and we're going to make that box more or less, even though it's not really a box, it's just 2 lines. But we're going to fill out all the columns. So remember that first column, in this case, the moment about a point, will always be ijk, always. So what we're going to do is we're just going to put I, and add the j, we're going to have the k. So remember about this too, the order of this operation matters. It always has to be the position vector cross the force vector. It can never be the force vector cross the position vector. You'll get different answers. They are not the same. So the second line here, this right here, has to be the position vector RAC. And we already have that. It's pretty easy. So we're just going to fill in the 6, 6, negative 4. And of course the last column, it has to be the force vector. So this can be force vector BC. And of course the values are a little bit long, so I'm just going to round them a bit, but don't worry, in the calculations they'll be accounted for. So we're just going to put 259, 490, and the last one is negative, and don't forget the negative or else you'll get, again, a wrong answer. So those negative signs are very, very important. So negative 231. So I was kind of an idiot. I drew the box small. It's probably better to draw the box a little bit bigger so that you can see your values a little bit more clearly. All right, so coming down here, remember there's 2 ways of solving this. One is the way where you just look at your formula sheet, because again, you'll be given the formula for this cross product. You will never have to derive it or anything like that. But let's just say for fun, yes, because this is what engineering is all about. It's just fun. We want to just figure this out manually. So what's going to happen is this moment will have 3 components, I, j, and k. So we can solve for each one individually. So let's just go m is equal to, I'll put in brackets. So let's figure out that I component first. So remember, when I'm figuring out these components, the first thing I do is find the component I want. So in this case, it's going to be I. I'm just going to cross out everything in that column. And then what I'm going to do is I'm going to make that fish. So I'm going to go 6 and negative 231, subtract minus 4 and 490. So right here, I went 6 and the negative 231, and then that's subtracted by the other 2. So negative 4 and 490. And the bracket, and that's my component in the I direction. So now moving on to the j. The one trick that you guys will always have to remember, and trust me, this will get a lot of students, is the j starts off with a negative. So negative brackets, I'm just going to erase the fish in the line. So in this case now, we're interested in that j direction. So let's cross off that column. Perfect. So now we're going to make the fish. So the fish goes from 6 to negative 231, and then negative 4 to 259. So I'm just going to write that in here. We want 6 and negative 231, and it's always minus, and it's going to be negative 4 times 259, and the bracket, and that will be my j component. So the next step is, of course, the last one, which is k. And remember, j is the only one that's negative. K is positive, and same with I. I and k have positive signs. It's only that j where you have to worry about that extra negative. So I'm just going to put in brackets, erase my old fish and my old line, and we're going to create the new line. So for this one, again, we're interested in j. We're not interested in j. I'm an idiot. We're interested in k. So let's just cross off everything in that k, and we go from 6 to 490, and then from 6 to 259. So I'm just going to write that down. We're going to have 6 and 490, and then minus 6 and 259. in the bracket, and this, and what we get is that's the k direction. And of course that's the last direction, so we can close the bracket. And then we have to put the units on this because of course it's a moment. So for force we're dealing with newtons, and then for the distances we're dealing with meters. So the units for this case would be Newton times meters. So this would be the final answer. Again, there's no variables involved. That is the final answer, but of course you're going to want to simplify it. You're not going to leave it like that. So what I do down here is I'm just going to go the moment at point A is equal to, and I'm just going to put in brackets, and I'm just going to do all of those calculations, nothing more. So what I get here is I get 574i plus 350j plus 1085k plus 1385 in the k direction. So I can end this bracket now. And remember, it has values of newtons times meters. So it's final answer. So let's just throw a box over top of it. Ta-da! I don't know how it went all the way down there, but the box still worked, and I got a box, so I'm happy. So this is the question. It's as simple as that, guys. I'm just going to erase this real quick. So it's as simple as that. You just have to pick your position vector that's nicest to you. And in this case, it's definitely A to C because the coordinates of C are really, really simple. But now, of course, a lot of you are going to go, okay, well, you said that I can pick any point. I could have picked B and got the same answer. And I know that some of you, of course, are going to go, well, I don't believe that. You're just saying that. It's not true. So we have time. Let's find out. So I'm going to do the exact same question again. What's nice is the force vector doesn't change. The only thing I'm going to have to find now is this RAB. That's the only thing I'm going to have to find that changes, because that force vector and Cartesian vector notation, it's good to go. I don't need to worry about it at all. So I'm just going to put a line here. And I'm going to go the moment, so this is the exact same moment, is going to be equal to RAB cross FBC. So again, we already know FBC, so to solve this again is actually as bad as the first time. We're already kind of a step ahead of the game. So the only thing we need to find is that RAB. So we know just by the formula it's going to be the coordinates of B minus the coordinates of A. And this is where it gets a little bit more messy because, as you guys know, the coordinates of B kind of suck. So what we have is 4 times the cosine of 45, and then we have 0j, and then we have 4 times the sine of 45. So those are the coordinates of B. And again, they're messy just because they have the cosines and the sines and stuff like that. And of course, we have to minus the coordinates of A, which we remember is 0, 0, and I believe 4. But I'm going to double check just to make sure. You always should double check. It is indeed 4. So we throw all this in. We get that RAB is going to be equal to, and we're just going to start the vector with the kind of the squiggle of brackets. And it's going to be 2.8828 in the I direction plus 0 in the J direction, and then minus 1.172 in the K direction. And that will be in units of meters. And this is where people start to get confused on how they're the same, because the force doesn't change. It seems weird that in an equation we just change one value, but the result is still the same. So it is really confusing. I agree, it took me a while to kind of wrap my head around it. If I were to prove it, I have no idea, if I'm being honest. Yeah, I'll just, hopefully that'll be your linear algebra prof showing you guys. But if we were to take the moment now, so the moment is going to be equal to, and we're going to draw that box, but I'm not going to be idiot this time. I'm going to give myself lots of room in the box, because why not? Remember that first row, always going to be a simple ijk. And then the second row always has to be the position vector. So in this case, we're going RAB. So now we're going to go 2.8, 0, negative 1.2. So I'm just putting these as only one decimal place, but in my calculations I'll take into account the remaining decimal places. So the force vector now that goes in the third row, that doesn't change, so we're going to get 259. Oops. 259. And then we're going to have 490. And my last one was negative 231. 231. And I'm just going to move the negative over, or else it looks like I'm going 490 minus something. So this is what we get. And again, we can find the moment rather easily now, just using what we know. So in this case, it's going to be in brackets, and we're going to start with the I component. So the first bracket, and I'm going to go down, draw my line. So I'm interested in I, so let's get rid of everything in I. I'm going to make the fish. So it's going to go from 0 to negative 231, negative 1.2, and 490. So I'm just going to write everything that I have. So it's 0 times negative 231 minus negative 1.2 and 490. In the bracket, and that's in the I direction. So the next direction, of course, is the J direction, but remember, please remember that it's always start off with a negative. So minus in brackets. I'm going to erase this so I can redo my fish. So interested in J, let's just cross out that J direction. And for the fish, we're going to go 2.8 times negative 231, come up, negative 1.2, and the 259. So right here real quick, we're going to have the 2.8. And the second one's negative 231. That's another thing too. Make sure you guys know the signs of everything that is in that column. And then minus negative 1.2 times 259. And the brackets, and that is my J component. And then finally, we can do the K component, which is positive. It's only that J component that's negative. So I'm just going to erase the previous fish, go to my last fish. So interested in K, so let's get rid of everything in that K. And we'll do the quick fish, so like this. And what we have is 2.8 times 490 minus 0 times 259. And that right there is in the K direction. So I can end the bracket now, and this of course will have units of Newton meters. I just got to make sure I put Newton meters above. Had a bit of a freak out there. Alright, so when I do all the math, what I end up with is the moment at A is going to be equal to, and then in brackets, 574I plus 349K, or sorry, J, 349J, and then plus 1,385K. So in the brackets, and our values in Newton meters. It's a final answer, so it's best just to toss a nice box around it to let everybody know this is the final answer that you arrive at. So this question is now done using the second way. So before we proceed, let's just take a look. So the I component, we got 574. We look up there, we also got 574. For the J component, we got 349. And up here we got 350. And now that's just rounding errors. Difference in how I put the numbers into the calculation. If I were to look more specifically, what I got when I found the J component was 349.4. So that's why it's rounded down. And in the first one here, I had 349.6. So it actually rounded up. So the difference was actually only 0.2. And then for the last one, I got 1385 for both of them. So both methods are valid, and that's a nice thing to know for the test. A lot of students freak out because they don't know which point to go to. The nice thing is you can pick any point you want. You can go to point B, you can go to point C. If there was a third point, you can choose that point. You'll always get the same answer and the correct value. So I hope that this tutorial helps you guys. This is the last one where we take the moment about a point. because as I was saying, this is kind of the beginning. Moment about a point, nice and simple. We're going to get into kind of more crazy things moving forward. The moment about an axis, finding specific coordinate points to give you to result in a specific moment, stuff like that. So this is just the beginning, guys, but these are the fundamentals. You know this, you'll be ready for everything moving forward. So thank you guys so much, and I'll see you guys in the next video.